right. Greetings, algebrains. We're going to try for another one-take wonder. I want to go over some of the stuff about inverse variation that we didn't get to this year, so I hope you enjoy. Inverse variation leads into this whole other family of graphs that you guys haven't even seen, and I want to get some coverage of it so that at least next year you're not going to be completely confused. All right. So, talking about inverse variation. Now, you guys remember direct variation, all right? So, we're going to take a little trip here, right? Down memory lane, we have direct variation that we learned, where you have y equals kx. K is that constant of variation, and equations with direct variation formed lines, and k was the slope of those lines. It was the rate of change, and all of that stuff. Just y varies directly as x, that bizarre language that you often hear, instead of just saying it's a direct variation equation. Y varies directly as x. Well, y varies directly as x increases or decreases. So in this case, k, your constant of variation. Okay. So now that we've had that little review, let's not let that confuse us. Okay, because we're going to need to think about some other stuff. So let's go down here, and whoa, that's way far down. Hold on here. Let's go down here and talk about what this actually is. Okay. All right. So two different situations here. Let me zoom out a little bit. Okay. Direct variation. We have this situation here with y equals kx. In inverse variation, it's y equals k over x. So in direct variation, there's no division here. Inverse variation, there's division. In direct variation, k is multiplied to x. And in inverse variation, k is divided by x. In direct variation, to solve for k, you did y divided by x, right? And in inverse variation, it's actually easier. To find k, you just multiply x and y. We're going to see how that works in a minute. In direct variation, k is like a slope, and in inverse variation, k, which is still the constant of variation, is very much not a slope. Very much not a slope. For direct variation, the graph is a line, and for inverse variation, let's just show you here, move that down a little bit, and zoom in. So we have a hyperbola. So direct variation goes through 0, 0. It's one of the ways you know it's direct variation. It's y-intercept is 0, right? And inverse variation, this is a hyperbola. And you'll notice that it has, in this case, this is the mother function here, y equals k over x. And it's got two lines where it never touches. Remember, we call lines like this asymptotes. It has a horizontal asymptote and a vertical asymptote, which in this case happen to also be the x and y axis. Okay, so these graphs are going to look very different from anything you've ever graphed before, but I don't want you to think that that means they're harder, because they're actually quite simple. So you better recognize inverse variation when you see it. Now, that does not mean that one of these is inverse and one is not. Sorry about the y's, they like to get cut off. This is not a v, it's a y. So let's look at these here. Get some annotation going. All right, so over here, we've got x is 1 and y is 16. X is 2 and y is 8. X is 4 and y is 4. Okay. Over here, we've got 1, input 1, output 3, input 2, output 6, input 3, output 9. Just from looking at this, we should recognize that between here and here, you're going to see a common difference, which you would expect in a linear function, right? This goes up by 3 each time. Each time, that is plus 3. So we know that we have a slope of 3 in this case. So we know that if this is some kind of variation and we have some kind of slope, then what we're dealing with is direct variation. We're looking at y equals kx. And since we know that slope is also indirect variation, our constant of variation, we can say that this line is y equals 3x. And we can test that out. Input a 1. 1 times 3 is 3. Input a 2. 2 times 3 is 6. And it works. Okay, so this one here, this input-output table is showing direct variation. Now I know how you guys are like, okay, so the other one's inverse variation. Yeah, of course. Surprise, it's inverse variation. Because if you tried to look here between this and this, 6, okay, so that's a difference of -8. And then from here to here, it's a difference of -4. I'm not sure that we're not seeing a pattern there. So that's not happening, but there is another pattern. So we know that's not a slope. Okay. There is another pattern here, and I don't know if you guys have picked up on it yet, but we talked about on the previous slide to find k, if you have y equals k over x, in order to find k, if I were to just solve for k, I would need to multiply both sides by x. So that gives us k equals x times y. Okay, well let's do x times y then. 1 times 16, okay. 1 times 16 equals 16. 2 times 8, wait a minute. Are we seeing the pattern now? 4 times 4 is 16. So what we're seeing here is we're finding the constant of variation for this inverse function here. So we know that k is equal to 16. And that's what's easy and nice about this is you can identify it if you notice that when you multiply x and y, it always comes out to the same thing. So that means that the equation for this one over here is actually, because k is 16, we just plug it in up there. This is the equation, y equals 16 divided by x. That's the equation, okay? So when we graph these, it also is nice because if you have a constant variation, you just think, what are the factors? And then you pick an x and a y in order to graph it. We'll see that in a minute. Let's look at this one here. Let's see. 2xy equals 10. Well, what kind of format can we get this into here? Maybe we need to have y on one side, so we're going to divide by 2x on both sides of our equation. And when we divide by 2x, we end up with y is equal to, well, 10 divided by 2 is 5, but 10 divided by x, that's just, we just got to stay down there. There's nothing we can do with it, right? Y equals 5 over x. So we know that this is not direct variation, okay? So it's inverse variation, right? Inverse. Okay. What about over here? X equals 2y. Okay, well, why don't I just divide by 2 over here? Get the y by itself. X over 2. So I have y is equal to x over 2, which x over 2, that's still just the same thing as 1/2 x, right? If you have a 1 up here, it would be 1/2 x. So this is just, and I'm going to flip the y to the other side here to make our life easier and symmetrical, the way we like to see it, y equals 1/2 x. So this is still direct variation. Okay? Nothing is being divided. There's no x in the denominator. Anytime there's that x in that denominator, you got to look out because it is not direct variation. It is inverse variation. Okay? So I'm going to clear this annotation here. Yeah, clear all drawings by drawings. And we're going to go on to the next slide here. All right. here we have, for those of you who like steps, the steps. And also, for those of you who hate the weird language, we have practice with the weird language, okay? So let's choose a cool color here. Let's pick dark green. All right. Assume that y varies inversely as x. The person who used to teach grammar and English in me just revolts at this phrasing, but this is how it's commonly, you know, as x increases, y varies inversely as x increases, okay? If, how about having a capital there? If y equals 18, when x equals 2, write an inverse variation equation that relates x and y. So they're looking for an equation, all right? They're looking for a y equals something, okay? Now we know, write the equation y equals kx. So you can just start with, if you want, just being like, okay, I remember I'm gonna do y equals k over x because it varies inversely. All right, plug in your values. All right, so my value is y is 18 and x is 2, so k over 2, and then we need to solve for k. So times 2 to both sides, and we have k is equal to 36. Now, this has not finished our problem. We've not solved the equation here. We've solved for k, but they're asking us to write an inverse variation equation. That means we actually have to give the equation, right? Yes, again, my y's get cut off. But we have y equals k over x, our k is 36, over x, and now you win. Right? Now, this is the very step-by-step option. The other thing you can do is once you're comfortable with this, you're gonna realize, wait a minute, this is pretty easy. If I just need to write an inverse variation equation, and we know that k in inverse variation is always gonna equal x times y, then all I have to do is 18 times 2, and I put that in my equation, all right? I'm just like, oh, okay, y equals 18 times 2 over x. So that's 18 times 2, so y equals 36 over x. My pen is not happy with me right now. There we go. Y equals 36 over x. All right. Clear those annotations. Scooch us down a little bit. Let's try talking about that product rule, right? This sounds wacky. If x comma y and x1, y1 are solutions for an inverse variation, then xy will equal x1, y1. Meaning, just like on that table we had back up here, if you have a point xy in an inverse variation equation, just like we had up here, we have a point xy. We have a point, where's my, annotate, there we go. We have a point xy, 1, comma, 16, and we have a point x1, y1, 2, comma, 8. This says that xy is going to be equal to x1, y1. That means 1 times 16 will equal 2 times 8. And it does. That's all that fancy thing is trying to say here. All right. So that's just the same thing we talked about. It's actually not too hard. You just multiply your x and y to get your k. All right. And if they're in the same, whoops, if they're in the same, go back. No, go forward. I lost my inverse variation. Come back. Oh, if only I could edit this out. Open up. Okay. So they are, that whole fancy, you know, rule is just telling you that if it's in the same direct variation equation, product rule for inverse variation, you can always find k by just doing k equals x times y. Okay, you'll know they're in the same equation if it's 1 and 16, 2 and 8. Okay, so let's look at another one of these. All right, zoom in again so we can just have a little more space here. It's nice to have a little zoom. All right. Assume, I know it doesn't look like y, but I swear it's y. Assume that y varies inversely with x. If y equals 3 when x equals 12, find x when y equals 4. Okay, the rule from the last page, we're going to use it. So we need to first find our inverse variation, okay? xy equals x1, y1, so 12 times 3, right, because they gave you 3 and 12. We're going to multiply our x and our y. 12 times 3 is equal to 4 times, we don't know. We have to find our x. X equals, all right. So 12 times 3 equals 4 times x. That's pretty darn simple. That's just 36 equals 4x. 36 equals 4x, therefore, you know, divide by 4, x equals 9. Just like that, okay? Win. So let's try again. Let's try another one. Let's try. Y varies inversely as x. Okay, so we know we have a y equals k over x situation. Y equals 4 when y equals 4 when x equals -8. Find y when x equals -4. Are these bugging you? I'll fix them. All right, so we know that we have a y value of 4 times our x value of -8. 4 times -8, and that's going to be equal to -4 times something. Cool. Well, 4 times -8. 4 times 8 is 32. And it's negative. So 32 equals -4x. So divide by that -4. And voila, we have x, just gonna move it up here, x is equal to +8. That actually kind of makes sense, doesn't it? 4 times -8, -4 times +8. Both of them equal the same thing. Okay, so I'm going to clear these annotations again and move on down to the next thing I'd like to show you. All right. Here we have word problems. Distance equals rate times time, the DIRT equation, d equals r times t, it's direct variation. However, if you're going to solve for time, what you're getting is t equals distance divided by rate. So it's inverse variation if the first one is direct variation. So let's try this. We'll probably need some calculators here. Sloan runs an average of 8 miles per hour and finishes a race in 0.39 hours. Miss Julie, that's me, finished the race in 0.35 hours. I probably cheated. I'm a really slow runner. What was my average pace? Okay, so we know that distance equals rate times time is direct variation. Give me my annotation back. Give me my name. There we are. Annotate. All right. So we know that distance equals rate times time is direct variation. And they're asking us, what was her average pace? Okay, I'm thinking we're asking about my average pace. I probably should have been clearer because, you know. All right. So an average of 8 miles per hour. In this case, that is Sloan's, let's see, average of 8 miles per hour. That per hour should give a hint. This is a rate. This per hour, per anything, always gives you a hint that that's your rate. Okay, so if that's your rate, then we have distance equals rate times time. And it also gives us 0.39 hours. Okay, so we don't know how far she went. Distance equals rate is 8 miles per hour times time is 0.39 hours. Okay, so now we can find our distance if we want to go to our little calculator, or I could just ask Alexa. Oh, darn it, I moved the Alexa out of my room. All right, well, we can do it the old-fashioned math teacher way. Let's do this. 0.39 times 8. Boy, you guys haven't seen this in a while, have you? 9 times 8. 3 is 24, 25, 26, 27, 28, 29, 30, 31. And then we have 2 decimals. Boink, boink. Okay, cool. 3.12 is equal to the distance Sloan ran, but that's still not really what we're looking for, is it? Instead, we're looking for my rate, but using Sloan's, I've now got the distance that we both ran because we ran a race, so we ran the same distance. So now what I'm going to do is I'm going to plug in my information into a inverse variation. Okay, I have time, so I have I'll put my 0 in front of it, 0.35. I'll actually change my color, that's really light. 0.35 hours, that's my time, is equal to my distance, which is 3.12 over my rate. Okay. Sorry, it's all crammed in with this. Distance over my rate. Look at that. Now all I have to do is solve to find my rate. Okay, and you see why it's an inverse variation, because you have a variable in the denominator. Okay, your variable is in the denominator. So some people are thinking, wait, if your variable's in the denominator, how do we solve this? The long answer, of course, is that you multiply both sides by r to get rid of the r over here, and then it puts an r over there. So that's one way to think of it. Multiply both sides by r. These r's cancel, and you're left with 3.12 is equal to 0.35 r. Okay. And then we're going to divide by 0.35. And I have my rate. Do I want to do that on the calculator right now? No, I don't. Okay. So that's just kind of an example of using direct variation and inverse variation in the reals. All right, next time I got to remember to have my calculator ready. Okay. Oh, we got to close this or it's not going to like me. Close this. All right, scrolling on down. Let's talk about graphing these things. All right, like I said, this type of graph is called a hyperbola. And we're going to use graph an inverse equation in which y equals 8 when x equals 3. So what we do know about this is we know that this equation has an 8 and a 3, and how do we find k? We just do 8 times 3, write the equation. K equals 24 because 8 times 3 is 24. So y is equal to 24 over x. Cool, we're going to be graphing y is equal to 24 over x. Second step, we're going to get to choose the values of x and y that we graph. Previously when you graphed, you might have been like, oh, let's pick -1, 1, and 0. Okay, fine. But for inverse variation, the easiest thing you can do is you look at your k and you say, what are the factors of 24? It's not a coincidence that I chose this as our first time out because 24 has tons of factors for us to graph. Okay, we're going to look for factors of 24. So what are factors of 24? 12 and 2, cool. 8 and 3, 4 and 6, 2 times 12, 0 and undefined. Because, yeah, I mean, there's 0 times nothing is 24, right? We can't actually do that, so 0 is undefined. That's because 0 is our asymptote. All right, so then of course you cannot forget your negatives because this is a hyperbola. You need a curve that goes this way and a curve that goes this way. So -2 and -12, -4 and -6, -8 and -3, -12 and -2. What I don't want to see is people only using positive values because it's only going to give you part of your graph. Okay, let's graph this. 12 and 2. So if x is 12, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 2, 1, 2. Okay, so we have a point there. this one. 8 and 3. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Cool. 4 and 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And 2 and 12. Look, we're coming back around, right? 12, 8, 4, 2, 12, 6. Yeah, all right. So 2 and 12 is 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now you notice that there's not an even space here because there would be another point in there, right? If we had, for example, 8, 3, that means we would also have 3, 8. Because they still multiply to 24. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. See how that completes our little curve there? All right, so now we have this, and we can just sort of, doing my best to fill these in. Okay, yeah, there we go, like that. All right, so it's gonna go off in that direction and up in this direction. And now we're gonna look, 0 is undefined, right? That's our asymptote. It's never gonna touch our asymptote. Do not touch your asymptotes. Then we have a -2 and -12, so that's not really gonna show up too well down here. Let's do -4, -6. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And -8, -3, 1, 2, 6, 7, 8, 1, 2, 3. All right, so these are kind of like, a little bit harder because I don't have enough room, but once you get the general idea of where these go, you can just kind of be like, okay, I kind of get the idea, right? It goes like, and then it kind of goes like that. If I had to, I could be more specific, but you know, limited space, limited time, and when you're graphing it yourself, I'm sure your teacher's not gonna make you do too many points, okay? Just a few points to get the general idea of where it is and where your asymptotes are, all right? Just look for those factors. If they give you a y and an x, they gave you a k. If they gave you a k, your points, your x and y values are those vectors. All right. Let's clear our annotations, clear all drawings, close that, and switch us down a little bit. Okay. Let's try it one more time with a little less prompting. Graph an inverse variation equation in which y equals 16 when x equals 4. Okie dokie. So y equaling 16 when x equals 4, we need to find out what k is. Okay, choose a fun color here. Let's go blue. All right, so k is going to be equal to, x times y. So in this case, our k is going to be equal to 64. So we now know that k is 64, so our equation is y is equal to 64 over x. That's our equation. That's what we're going to graph. Now that k, we have to find factors of 64 to graph. Now, do we want to graph 1 and 64? Heck no. Who wants to do that? That's no. So let's just pick some x and y values that work nice and well for us to sort of give us the general idea of this. Of course, we have 8 times 8, 8 and 8, 64, and we also have -8 and -8 are 64. We have, of course, 4 and 16, and we have 16 and 4, and we have -4 and -16, and we have -16 and -4. Cool. All right. So this might be just enough points to kind of give us the general idea for how to graph this. Okay, we know we have a point at 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And we have the same thing on the opposite side. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Cool. We've graphed these. 4, 16. Okay. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. And 16 and 4. So if this is 8, 1, 2, 3, 4, 6, 8, 1, 2, there we go. Okay, so you can start to see where the curve is already on this. Okay. We don't have to do 1,000,001 things. Well, that was kind of bad, but to sort of get the idea of where this is going. And this will gradually decrease until it gets close to its asymptote. All right, and the same general idea here. We have that's 8, 9, 10, 11, 12, 13, 14, 15, 16, 1, 2, 3, 4, -4. So you can kind of get the gist that this is also going to go here. Yeah, it's going to curve down, and it's going to kind of go down there, off into the distance. I didn't really leave myself enough room, but you can see our hyperbola forming up. Okay, it's not too bad. Factors of K, X and Y, positive and negative. Graph a few points, rock and roll. Clear my annotations, and I'm thinking we're close to the end here. Let's see. Yeah, Mother Function Project is fun. You guys have talked about that, and that's all that is. So I hope you enjoyed this, and it gave you a brief overview of what inverse variation is, what it looks like on a graph, how to graph it, and a little bit of how it might be used in everyday life from time to time. Stop my share, say bye-bye, and let me know if you want extra materials on this. I can find some for you.